This is section 4.6, day 2, and we're going to look at a few applications of related rates. Before we jump into the examples, I want to have just a short discussion about trig and SOHCAHTOA, and we're going to use this strategy to make the math easier. So this isn't your notes, just kind of sit back and go through this review. So when we're talking about right triangle trig and SOHCAHTOA, we're talking about, making a sketch and seeing that there's a right triangle in the sketch. So for instance, like a ladder leaning against a wall. If we know the ladder is 25 feet long, and then when it leans against a wall, we have a distance along the wall and a distance along the ground. So let's say we take this 25-foot ladder and prop it up, and it hits the wall 24 feet up. How far is it? How far is the foot of the ladder from the base of the wall? And so we have got a right triangle here set up in the picture. And of course we can use Pythagorean's theorem to find x. So if we do x squared plus 24 squared equals 25 squared, when we solve that, we'll get a value of 7. So when we set up a ladder then and lean it against the wall, we know that it makes an angle theta with the ground. And so now we can set up our SOHCAHTOA, our right triangle trig, to find the 6 trig functions. So if you remember, sine is opposite over hypotenuse, so that's 24 over 25. Cosine is adjacent over hypotenuse, so 7 over 25. Tangent is opposite over adjacent, so that's 24 over 7. And then the other 3 are reciprocals of the first 3. So cosecant is reciprocal of the sine, secant is reciprocal of the cosine, and cotangent is reciprocal of the tangent. And so I know you've done this in several courses before reaching calculus. The nice thing is we can use these ratios instead of using the trig in our problems. And that makes it really convenient because then we never need to know the angle theta. So if this ladder starts to slip down the wall and I want to know how this 24-foot dimension is changing, then I can use, let's say we set up a sine ratio, I can use the ratio 24 over 25 for this particular problem instead of sine of the angle, and then we can avoid using the angle measure altogether. So let's see how we can use this in a related rates problem. Okay, so let's try this example here. We've got a ladder, and we placed the ladder against a wall here, and we placed it too far away at the base, so the base of the ladder starts sliding this way, which causes the top of the ladder to start sliding down. So we can see the right triangle here. And in this right triangle, we're going to have this dimension along the wall decreasing while the base along the floor increases as this ladder slides. So that's the related rate scenario. As this ladder goes into motion, these 2 dimensions are changing. The ladder, though, is 13 feet long, and that's not going to change. So if we call the base of the right triangle x, we know that this base is getting bigger as this ladder slides, and that's what this is saying right here. The base is moving at a rate of 5 feet per second, so we know that the rate of the base, the dx dt, is 5 feet per second. And we don't know what y is, and for this part of the problem, we're not too concerned about it. We're going to just deal with the information that we have here, that this is 5 feet per second. And so since we have the rate that the base changes, we're going to incorporate the base and the fact that this is a constant 13 feet, and we're going to make a trig ratio out of these 2 sides. So the reason why I'm picking these 2 sides again is because the 13 feet is constant, and the x is the thing that we have some information about here. And so as this ladder slides, then this angle theta starts to close up. And we want to know, that's what the question is here, we want to know how fast that angle is closing up. So we're going to, like I said, we're going to set up a ratio here. So this is the adjacent and the opposite side, or excuse me, the adjacent and the hypotenuse side. So in our attempt to find d theta dt, how quick this is closing up, we're going to set up the cosine ratio. So cosine is adjacent over hypotenuse, x over 13. And what I'm going to do is I'm going to rewrite this. I'm going to just a quick reminder that x over 13 is really 1 over 13 times x. This helps us differentiate. So now we're going to take the derivative. So in a related rates problem, we take the derivative of both sides. So the derivative of cosine is minus sine theta. And then the derivative of this is just going to be 1/13 x is the same as like saying 3x. So the derivative is just going to be 1 over 13. Oh yeah, and then we need a d theta dt, excuse me. So we need our related rate, d theta dt. And then we have 1/13 times dx dt. So here's our related rate derivative. So we took the derivative of cosine got minus sine d theta dt to make it a related rate problem equals 1/13 dx dt. So this is what we're trying to find here. We know this is 5. And so when we're talking about minus sine theta, now you would think, well, gee, I need an angle measure here. We're going to sidestep that. So we need to get information in order to replace the sine of theta. In order to replace the sine theta with a fraction, we need to get information about x and y. So that's what our still shot is going to do. So we know when we have a rate of 5 feet per second, we have an x value of 12. So we're going to pull that into the picture now. And then since we have these two sides, we can find this using Pythagorean's theorem. So our still shot is a 13-foot ladder, that's part of the problem statement, that is 12 feet from the base of the house. So we're going to put 12 feet in there, and that only happens instantaneously, but we need the still shot, the snapshot, so to speak. So if I have these two pieces of information, I should be able to see how far the ladder is up on the wall at that point in time by doing the Pythagorean's theorem. And I need this because I need, and remember in the related rates expression we have a sine of theta, so I need the opposite side here. So I definitely need that. So I set up my Pythagorean's theorem. 12 squared plus y squared equals 13 squared. So 12 squared plus y squared equals 13 squared. And I go ahead and solve it. So I get a y value of 5. So we know that the ladder is 5 feet off the ground. Its base is 12 feet from the wall. It's a 13-foot ladder. It only has this position instantaneously as it's moving. But I need that information for my related rates equation. So now, looking at that, let's set up some ratios. So we know the cosine is adjacent over hypotenuse, that's 12/13. We know the sine is opposite over hypotenuse, that's 5 over 13. So we're going to substitute these ratios into our equation as needed. So remember our related rates expression was minus sine d theta dt over equals 1/13 dx dt. So what we're going to do then is we're going to substitute this in. So we have minus 5/13. So instead of trying to figure out what theta is, I just took this whole ratio, 5/13, and put it in for sine, since these two expressions are equal. And so that's going to equal, and then times d theta dt, that's going to equal 1/13 times dx dt, which is 5. So mathematically then, working that out, we get a d theta dt of minus 1 radian per second. So what does that mean? Well, that means the negative sign means that this angle is closing up or getting smaller, and it's getting smaller at 1 radian per second. Remember, a radian is about 60 degrees. So, so that's a way to use SOHCAHTOA to avoid having to find an angle measure in a related rate problem. Here's another related rate problem, and in this related rate problem, we know the angle here. So we're going to use SOHCAHTOA in a slightly different way. So what are we given here? We've got a hot air balloon. It's rising straight up from a level field and is tracked by a rangefinder 500 feet from the liftoff point. So here we are. Here's the liftoff point, and we're 500 feet away. And we want to know what's happening at the moment that the range fielder's elevation angle is a pi over 4. So a range fielder is looking through the scope up at the balloon, and it's kind of like a surveyor, if you've ever seen a surveyor on the side of the road. And their viewer is angled at pi over 4, and we know that is 45 degrees. And we also know that as this balloon rises at this instance, the angle has to be rotated 14/100ths radian per minute to keep tracking the balloon. So we want to know the balloon's velocity, how fast it's rising. In other words, how quickly the height is changing at that moment. So we know theta is pi over 4. We know d theta dt is 14/100ths radians per minute. And so we're going to go ahead and set up, with this information, we're going to set up an expression that we're going to differentiate into our related rates expression. So we want to find how fast the balloon is rising at that moment, and that's dH dt. How fast is a rate? So it's the rate of change of height that we're looking to find. Okay, so we need to set up then a relationship that connects theta and dH dt, so these two values. And then we always want to try to tie in a value we know. So we know this is 500 feet. So in other words, we don't know this value. So we're going to try to leave that out of the calculation. So if we use these three pieces of information, and I replace that with a pi over 4, if we use these three pieces of information, we can set up a trig ratio. And so this is opposite and adjacent. We're going to set up the tangent to pi over 4. This is going to get us our snapshot. And so the tangent of pi over 4 equals h over 500. So we know we have an h value of 500 feet. That's our snapshot. Now we can go on then to our related rates expression. So our related rates expression is to think of this as a theta again, because this is actually actively changing as the balloon rises. And so tangent of theta equals h over 500. So we can keep this a 500 because this is not changing, but h is changing as the balloon rises. So we put the variables back in here so that we have an expression that we can differentiate. So we're going to differentiate this. And to make the calculus easier, again, we did this in the last example, we're going to think of h over 500 as 1/500th h. In other words, this is just a coefficient. These ratios you can always use the quotient rule on, but that gets really to be more work than is necessary. So we're going to think of this as just a coefficient of 1/500th. So we know that h and theta are both changing. We know that the 1/500th is not changing, it's a constant. And so as we differentiate, the derivative of tangent is secant squared. So we have secant squared d theta dt, that's our related rate. We have to have that because our theta is changing. And that equals 1 over 500 times derivative of h, which is dH dt, or some people think of that as 1 dH dt. But the value 1 wouldn't change this expression. So we have our related rates expression now. And remember, we're trying to answer how fast is the balloon rising. We're trying to find this value. Okay? So in this situation, since we have a theta, it's pi over 4, we can substitute that value in. And we have our d theta dt, it's 1400th radians per minute. We can find our dH dt. Okay, so the first thing I'm going to do is multiply both sides by 500. Those are going to cancel. So now I have dH dt equals 500 times secant of pi over 4 quantity squared. Notice I moved the power to the outside here that's mathematically equivalent, times d theta dt, which is 14/100. So now this is how we're going to use our SOHCAHTOA here. We don't have a secant key on our calculator. And in fact, this would be a no calculator question anyway. So we got to remember the unit circle here. So we know that pi over 4 is right here. So we're dealing with these cosine and sine values. And we know that the secant of pi over 4 is the reciprocal of the cosine of pi over 4. Okay, and so on this unit circle here, remember that these ordered pairs are x comma y, but they're also cosine comma sine. So for cosine of pi over 4 is root 2 over 2. So if the secant is the reciprocal of that, then the secant has got to be 2 divided by root 2. So that is what we're going to put in for secant in our related rates equation. So coming back to the related rates equation then, we're going to have 500, and instead of secant of pi over 4, we're going to put in 2 over root 2. We're going to square it, and then we're going to multiply by 14/100. And yes, this can actually be done without a calculator. So let's start by first squaring this. So when we square this, we get 4 over 2. And we know 4 over 2. We can simplify that as just 2. And now I'm going to go ahead and multiply 500 times 2, because that's easy enough to do. 500 times 2 is 1,000. And 1,000 is a really convenient number, because 1,000 just causes this decimal place to move over 3. So if we move this decimal places over 3, then we end up with 140 feet per minute. So at the time that this h is 500 feet, we're moving upward at 140 feet per minute. So this is just, again, a variation of using the unit circle and SOHCAHTOA to make the math easier on the related rates expression. So just a summary then of section, this is actually section 4.6. I don't know why I have 4.3 here. How can the derivatives be used to evaluate rates? Derivatives are instantaneous rates. And the way we evaluate them is we need to use implicit differentiation and the chain rule to get our related rates expression. And then we could actually add on here using our SOHCAHTOA skills to handle right triangle applications. So at this point, you should be able to do the day 2 homework. If you would like to take a Blackboard quiz instead of doing the homework, you can do that at this time.